Okay, good day, everybody. So to those who missed the lecture about the basic concepts, so I'm doing this live stream for you to be able to review as well in preparation for your first problem set. So let's review the basic concepts in differential equations. Okay, so what is a differential equation? So a differential equation is an equation that contains derivatives of one or more unknown functions. So this unknown function is also known as the dependent variable, with respect to one or more independent variables. So we have here three examples of a differential equation. So the first example here is dy over dx equals cosine of x. So this is a differential equation since it contains a derivative in it. The second example is x squared plus y squared times dx minus 2xy dy equals 0. So as you can see, it contains differential. So this is also considered as a differential equation. And the last example here is a differential equation since it contains derivatives, specifically partial derivatives. Now let's go to the classification by type. So we have the ordinary differential equation, or ODE, and partial differential equation, or PDE. So when we say ODE, or ordinary differential equation, it contains ordinary derivatives of one or more unknown functions with respect to a single independent variable. Now, for partial differential equation, it contains partial derivatives of one or more unknown functions of two or more independent variables. So take note for ODE. So the unknown function is dependent to only one independent variable or single independent variable. While for partial differential equation, it has two or more independent variables. Now let's go over the first type. So here we have dy over dx plus y over x equals x squared. So this is an ordinary differential equation since it contains an ordinary derivative, the dy over dx. So in this equation, the dependent variable is y and the independent variable is x. Okay. Another example of an ODE, or ordinary differential equation, is dx over dt plus dy over dt equals 2x plus y. So the dependent variables here are x and y, and the independent variable is t. So remember that ODE has only one independent variable. Now let's go to the next type, which is the PDE, or partial differential equation. So this contains two or more independent variables. The first example, so this is the symbol of partial derivatives. So this is second partial derivative of v with respect to x plus the second partial derivative of v with respect to y equals 0. So in here, the unknown function or the dependent variable is v. And the independent variables are x and y. So as you can see, there are two independent variables. The next example is a PDE since it contains partial derivatives. And these are partial derivative of u with respect to x and partial derivative of v with respect to y. So it's an equation since it has an equal sign. Now there are two dependent variables or unknown functions, and there are also two independent variables. Okay. Now for the notation, so these derivatives, okay, are known as the Leibniz notation. So you can write the first derivative as dy over dx For second derivative, so we have d squared y over dx squared, or you can say second derivative of y with respect to x. And the third example here is third derivative of y with respect to x. So this is the Leibniz notation or Leibniz notation. Another way of writing the derivative is the prime notation. So y prime means the first derivative of y. And y double prime is second derivative, y triple prime is third derivative, and so on. Okay, so to further explain, dy over dx is in Leibniz notation, and y prime of x is in prime notation. So this means that in y prime of x, y is the unknown or dependent variable, while x is the independent variable. Okay, for dv over dt, you can write in terms of the prime notation. So dv over dt can be written as v prime of t. V is the dependent variable and t is the independent variable. Now, the third derivative, the third example here is second derivative of y with respect to x can be written as y double prime of x, or simply y double prime. So again, the dependent variable there is y and the independent variable is x. Okay. Now, it's important that we know the order and degree of a differential equation since we'll be dealing with a differential equation. So if you know the order, then you will have an idea on how to solve that particular differential equation. So let's define first what is the order of an ordinary differential equation and the degree. So when we say order, it is the order of the highest derivative that appears in the equation. Okay, and the degree of an ODE or ordinary differential equation, it is the algebraic degree or exponent of the highest order derivative after clearing off all the fractional exponents that you can see in the equation or specifically in the derivatives. Okay, let's have an example. So we have this differential equation, y double prime of x plus y prime of x raised to 2 equals x. Okay, as you can see, this is a differential equation since it contains derivatives. Now, we need to know what the order and degree of this differential equation. So you must take a look at the highest derivative that you can see in this equation since y double prime of x is the highest derivative in this equation, and y double prime means second derivative. Therefore, the order of this DE is second order. Okay, so we are right. Now, it is first degree since the exponent or power of this highest derivative that you can see, okay, is 1. Therefore, the degree of this differential equation is first degree. Okay. Always remember that you must look into the highest derivative for you to say what the degree of that differential equation is. Now, next equation. So third derivative of y with respect to x raised to 2 equals first derivative of y with respect to x raised to 5. So this is again a differential equation since it contains derivatives. Now, the dependent variable here is y and the independent variable is x. Okay, now, to determine or obtain its order, so you must look into the highest derivative. So as you can see, third derivative of y with respect to x is the highest derivative that you can see in the equation. So therefore, the order of the differential equation is third order. And since the exponent of this highest derivative is 2, then the degree of this differential equation is second degree. Okay? If you have any questions, just comment down below. Now we have another example here. Y double prime raised to 1/2 equals x times y. As you can see, this equation contains fractional exponent. Again, we can determine the order. However, for the degree, we must clear off fractional exponents. Okay, so what do we do? To eliminate this 1/2 in the exponent of y double prime, so we need to raise the entire equation to 2. So 2 times 1/2 becomes 1. Therefore, the equation will be y double prime equals, on the right side of the equation, since it's being raised to the power of 2, this becomes x squared times y squared. Now that we have eliminated the fractional exponents, then we can say that the degree of this differential equation, since there's only one derivative and that is second derivative, therefore the order is second order and the degree is first degree. Okay, another example. So give the order and degree of, okay, we have square root of y prime equals 3 times y triple prime raised to 2/3. So as you can see, there are fractional exponents in this given differential equation. So let me share to you my whiteboard so I can show you how to eliminate or to free this DE from fractional exponents. Okay, let me write again the equation. So we have square root of y prime equals 3 times y triple prime raised to 2/3. So this left side of the equation, square root of y prime, can be written as y prime raised to 1/2 equals 3 times the quantity y triple prime raised to 2/3. Okay, for the order, we can be able to obtain the order since we're going to look at the highest derivative, and the highest derivative here is third derivative. So it's clear that the order is third order. However, for the degree, we need to make sure that there are no fractional exponents in it. So now we're going to raise the entire equation to a number that will make the exponent of these derivatives a whole number. Okay, now think of a number or that will make these fractions a whole number. So if we put 2 here, so the left side will only be the part of the equation that contains whole number. However, for the right side of the equation, it will have fractional exponents. So the closest number that we can multiply to the fractional exponents is 6. Okay, so raising the entire equation to power of 6 will make both sides of the equation, both derivatives of the equation, having whole number exponents. So y prime, okay, raised to 1/2 times 6, it will become 6 over 2. 3 raised to 6 for the right side of the equation, and for y triple prime, so we have y triple prime raised to 6 times 2 is 12 over 3. Now we simplify. So the left side will become y prime raised to 6 divided by 2 is 3. So now we have a whole number exponent equals, just copy 3 raised to 6 since this is the constant. And here 12 divided by 3 is 4. Therefore, we have y triple prime raised to 4. Okay, as you can see, the equation now does not contain fractional exponents. Then it's clear that we can say the degree of this differential equation is 4th degree. So why 4th degree? So take a look at the highest derivative. It's third derivative, and the exponent of this third derivative or power of this derivative is 4. So we can say this is a third order differential equation, 4th degree. Okay, one more example. So let me think of a DE. For example, I have dw over dt raised to 5 plus second derivative of w with respect to t raised to 3 plus third derivative of w with respect to t raised to 2 equals 0. Okay, so take a look at the equation. So to find for the order, you must look at the highest derivative in the equation. So we have first derivative, second derivative, and third derivative. Since the third term contains the highest derivative, which is third derivative, then the order is third order. Now for the degree, so degree is the exponent of the highest derivative appearing in the equation. So you cannot say that it is fifth degree. Okay, looking at the first term, so ito yung pinakamataas. This is the highest exponent that you can see, but dw over dt is not the highest derivative. Therefore, you just look into the highest derivative that appears in the equation, and that is the third derivative. And the exponent of this is 2. Therefore, that will be the degree of the equation. So this will be third order, second degree. Now, if you're asked, what is the dependent variable of this equation? Okay, the dependent variable or the unknown function is w. So you can write here, dependent variable is w, and the independent variable here is t. Okay, so now let's proceed to the next part of our discussion. Okay, now let's go to the classification by linearity. So how can we know that the DE is linear or nonlinear? So first, let me show you the linear form of the nth order ordinary differential equation. So the unknown function here is y. So the variables involved here are x and y. So as you can see, we have coefficients in each term. So a sub n of x, a sub n minus 1 of x, we have the ellipsis, a sub 1 of x, a sub 0. So these a's here are function of x. On the right side of the equations, we have f of x, a purely function of x. And take a look at the derivatives in each term, including the unknown function. So nth derivative of y with respect to x, n minus 1th derivative of y with respect to x, first derivative, and y as the unknown function. So what can you say about this equation? So it is said to be a linear differential equation. So our first property here, so that equation is said to be linear if the dependent variable y and all its derivatives, y prime, y double prime, and so on, are of the first degree. So when you say first degree, so the power of each term must be 1, including the unknown function. So take a look at the nth derivative. The exponent of this derivative is 1. This derivative, the power is 1. First derivative, the power of this is 1. And the variable y is 1. So that's the first criteria for you to be able to say that this is a linear differential equation. Okay, second property. So the coefficients, or the function a sub n of x, where n is from 0, 1, 2, 3, and f of x are known and depend only on the independent variable x. So otherwise, the ODE is nonlinear. Remember that the independent variable here is x. So these a's here are known and a function of x. Now let's have some examples. Before that, we have also nonlinear functions. So examples of nonlinear functions are trigo functions, sine of y, cosine of y, exponential functions also. So An ordinary differential equation is said to be nonlinear if it contains, these functions. Okay, so the unknown function is of the form of trig function or exponential function. But if these nonlinear functions refer to the independent variable, so still the DE is said to be linear. Let's have an example to clearly understand the linearity. Okay, so the first example here, y double prime minus xy double prime plus 3y prime equals x. So the idea of this example is to determine whether this DE is linear or not, since the power of each term, the power of the derivative, including the unknown function. So we don't have y here, so just the derivatives of y. We have y double prime, the power is 1. Y double prime, the power is 1, and y prime, the power is 1. And on the right side of the equation is a pure function of x. Then this is a linear differential equation. Okay, so there are no nonlinear functions in it. And the coefficient of this y prime here in the second term is a function of x. So still it follows the property for linearity. Now, for the second example, this is a non-linear differential equation. Now, why? As you can see, the unknown function y or the dependent variable y is of this form, trigonometric form. So sine of y. This makes the equation non-linear because sine wave or sine function is, it's a waveform alternating. Although you have a derivative that contains a power of 1, but having this term, sine of y, makes this equation non-linear. Now for the third equation, y triple prime, so the power is 1, 3y prime, the exponent is 1, 2y, okay, y raised to 1, okay, equals x squared. The right side of the equation is a pure function of x, and all the derivatives of y, including the unknown function, the power is 1, then it is a linear equation. So I've put here the order, third order. So it means that that is the highest derivative that you can see. So third derivative is the highest derivative in this equation. Okay, fourth example. So y double prime plus 4y prime plus 2y equals e raised to y. So it is nonlinear. Why nonlinear? As you can see, we have an exponential function here, e raised to y. And y is the unknown function. It should not be done for the equation if you want to make it linear. So here we have, and the right side should be a pure function of the independent variable. So that's another thing. Okay, although the power of each term of the derivative of y, including its unknown function, is 1, but because of this exponential function at the right side of the equation, makes this equation a non-linear ODE. Okay, maybe for the, going back to this example, if this is e raised to x, then we can say this is a linear differential equation, since the involved function at the right side of the equation is a function of x, and e raised to x. But since it's e raised to y, and y is the dependent variables, it will not be a linear equation. Now, for the next example, we have sine of x times y triple prime minus cosine of x times y prime equals 2. So as you can see, the derivatives have coefficients and sine of x and cosine of x. And sine of x and cosine of x are functions of x, or function of x. Then take a look at the derivatives. What are the exponents or power? It must be 1 to make it linear. So y triple prime has a power 1, y prime has a power 1. Therefore, this equation is linear or linear differential equation. Okay, and this is third order since the highest derivative that you can see is third derivative. Okay, so any questions? Okay, I hope it's clear. Now let's proceed to the solution of an ordinary differential equation. Now, a solution of an ODE is a relation connecting independent and dependent variables which satisfies the differential equation. Okay, for example of a solution. So the equation y equals c times e raised to 2x is a solution of y prime equals 2y. Why is that? Okay, so we have c here. C is an arbitrary constant. So an arbitrary constant is any constant or any value. So it could be 1/2. It could be square root of a number, the constant. Okay, so let's take a look at this example. So why this equation y equals c e raised to 2x, a solution of y prime equals 2y. Since y prime, okay, equals 2 times c e raised to 2x. Okay, so what happens here? We are going to differentiate this equation. Okay, so differentiating y will be y prime, and differentiating this side of the equation. So you copy the constant and then copy e raised to 2x and differentiate 2x with respect to x. We have 2. That's why we have 2c e raised to 2x. Now, dividing both sides of the equation by 2 will result to this equation. We'll have y prime right over 2. We're able to eliminate 2 here on the right side of the equation. So we have c times e raised to 2x. Now, since in the original equation we have y equals c e raised to 2x. So we can plug in here. Okay, we can replace c e raised to 2x by y. That's why we have this equation. So y prime over 2 is equal to y. Okay, it's equal. So y is equal to c e raised to 2x in this given equation. Now simplifying, we have y prime equals 2y. That's why it's correct that the solution of y prime equals 2y is y equals c e raised to 2x. Okay, so that is an example of a solution of an ordinary differential equation. Now we have two types of solution, the general solution and the particular solution. So the general solution is a solution containing the number of arbitrary constants equal to the order of an ODE. Okay, so the general solution contains an arbitrary constant represented by C. The particular solution is a solution obtained from the general solution by giving particular values to the arbitrary constants. So once the value of the arbitrary constant is obtained and no arbitrary constants that can be seen in the solution, then that is a particular solution. So you can only get the particular solution if you use the general solution, applying the conditions to solve for that value of the arbitrary constant. So general solution contains an arbitrary constant, and then you use the general solution to determine the particular solution. So let's have an example. Determine the particular solution of the given ODE x dx plus y dy equals 0 when x is equal to 0 and y is equal to 2. So we have a differential equation and a condition. So this condition will help us determine the particular solution. So if we solve this equation, we will first arrive at its general solution. And afterwards, to determine the particular solution, we need to use these conditions, okay, to solve for the value of the arbitrary constant. Okay, let me copy first and we will solve this. So we have the condition x is equal to 0 and y is equal to 2. So let me, okay, go back to the whiteboard. Okay, so we are asked to determine the particular solution. So the given equation, differential equation is x dx plus y dy equal to 0, and we have a condition. So we need to have a condition for us to be able to determine the particular solution. So x is equal to 0, y equals 2. So firstly, so how do we arrive at that solution of a DE? So we are going to integrate. So we integrate each term. So integrate the first term, x dx, plus the integral of y dy equal to, okay, so what happens at the right side of the equation? So this will be, yeah. So when you integrate, you have a plus c, or plus the arbitrary constant c. So you put c at the right side of the equation. Now integrating the first term, and this is a pure function of x, that's why the answer here is x squared over 2. So using the power formula, or power formula for integration. Okay, so second term, so integral of y dy, we have y squared over 2 equal to c. Since both of the terms have 1/2 or has 2 in it, so we can actually simplify this equation. So we are allowed to do this in simplifying the equation. So we, instead of writing c, we can put c over 2, then simplify the entire solution or equation of this DE. So since I said earlier that an arbitrary constant could represent any number, so we can actually utilize, or we can replace the representation to simplify the solution. So we can do whatever we want to that arbitrary constant. We can introduce another constant to simplify the entire solution or equation. So except for, putting variables in the arbitrary constant, is not allowed. So you can only say square root of c, that's allowed, for as long as you can simplify the solution. You can put 1/2, you can put c squared if all of the terms have or has a power in it. So in this case, each term has 1/2, 1/2, so I can put also 1/2 to the right side of the equation involving the arbitrary constant. So since each term has 1/2, then I will multiply the entire equation by 2. So making each term, we have x squared, we eliminate the 1/2 there, plus y squared equals c. So this is now the general solution. Okay, now we are after the particular solution. So these conditions, okay, this x equal to 0, y is equal to 2, will allow us to solve for the value of the arbitrary constant c. So let me just change the color. Okay, so solving for the particular solution, so applying the condition x equal to 0, so we have 0 squared plus y is equal to 2, so 2 squared equals c. So 0 squared is 0, 2 squared is 4, therefore the value of the arbitrary constant is 4. Therefore, the particular solution is x squared plus y squared equals, so the particular solution does not contain an arbitrary constant. So you just plug in the general solution, the value of that arbitrary constant. So we have this. Okay, this is now our particular solution. Now, particular. Are you familiar with this equation? This is actually an equation of, let's go back to, okay, so x squared, just a trivia, plus y squared equals 4 is an equation of a circle. Okay, so this 4 here is the square of the radius. So if you recall, x squared plus y squared is equal to r squared. This is an equation of a circle. So the radius here, so r squared is equal to 4, therefore the radius is equal to square root of 4 is 2. So you can actually put an illustration here. Okay, this is a circle with center at the origin, so the radius is 2. So now 1, 2. That is how you illustrate this equation. Okay, so for this equation, so pwedeng bumalik naman. If you want to know the differential equation, so we simply differentiate. So we have x squared plus y squared equal to r squared. Okay, this is a parameter or the radius here. That will be our next topic. So let's determine the DE. So we can only differentiate depending on the number of parameters that we can see in the equation or in the solution. Since it only has one parameter, it means that the value of the radius represents one circle. So that is the parameter here. So we will differentiate only once. And this is a bonus lecture anyway. We'll talk about this on our next topic. So x squared differentiate with respect to x. So we have 2x times 1. Okay. Differentiate y with respect to x. So we have 2y y prime equals, so differentiate a constant, and 0. Or dividing the entire equation by 2 to simplify further. So moving on here, so we have x plus y prime equals 0. Now this y prime can be written as dy over dx. Okay. So multiplying both sides by dx, we have x dx plus y dy equals 0 times dx is 0. So as you can see, we go back to the differential equation. So this are given earlier in the last example that we had. Okay, so that's all for now. We'll meet again for our next topic.